So now that we know how to add vectors, whether they're in a straight line at a 90-degree angle or at a non-90-degree angle, we need to put in that last piece of the puzzle. So when our two vectors are at a 90-degree angle, we know that we can add them using Pythagorean theorem, and we can find the angle of the resultant using SOHCAHTOA. The problem is when we have two vectors at a non-90-degree angle, we can add them using law of cosines, but we have no way of knowing the angle of the resultant. So what we're going to look at today is a way that we can find the angle of the resultant adding two vectors at a non-90-degree angle. So the way we're going to do that is adding our vectors using what's called components. So in order to figure out how to use components, we're going to have to go through a few key pieces of adding vectors. The first one is how we look at the angles. And we've been doing this a little bit, but we want to make sure that we're doing it right when we do components. When we look at the angle of the vector, we're always measuring our angle counterclockwise from the x-axis. So here's our x-axis, and we're going counterclockwise from there to measure the angle of our vector. Notice even though there's a little triangle here, the vectors or the angle's not inside of that triangle because that wouldn't be counterclockwise from the x-axis. Okay, so we're always going to go counterclockwise from the x-axis to measure the angle of our vectors. Okay, so when we look at the components, we're doing something called vector resolution. So if you think of what the word component means just in everyday language, it means pieces. So if you think of your vector as the main piece of the puzzle, right, or as the slope, if you will, then we have our two components are the pieces that make up that main vector. So if we look at this one down here, our vector is 19.8, whatever, we don't have units, so we'll call it meters. So it's 19.8 meters long. But to get there, we could have gone 13 meters towards the east and then 15 meters towards the north, right? So that's what we had been looking at, is being given the two vectors and finding the resultant. Vector resolution is kind of like going backwards from there, is being given our vector and then finding the two pieces that went into that vector. So it's like rise and run, right? How far over did you have to go on the x-axis and how far did you have to go on the y-axis? So you'll notice over here we had to go in the negative direction on the x-axis, so our component is negative. We went positive on the y-axis, so our y component is positive. Over here, we went positive on the x-axis, so this is positive, and positive on the y-axis, so this is positive. So our components are really just showing us how far to the left or right did we go on the x-axis, and how far up or down did we go on the y-axis. So if we look at this blue vector would basically be like our resultant in this case. And then here's our x component and our y component. So we can use SOHCAHTOA to solve for each of these sides. So I know it says f over here and a over here, but you get the idea. So to solve for the x component, we would use cosine. So the cosine of theta, right? Remember cosine? So COHCAHTOA, cosine is adjacent over hypotenuse. So the cosine of this angle, this 40 degrees here, would be the adjacent side. So that would be f of x, right? Or we put a of x to make it a little broader over here, divided by our hypotenuse, which is a, our main vector. So if cosine theta equals ax divided by a, adjacent divided by hypotenuse, we can multiply both sides by a to get ax by itself. So that's where our main formula for the x component of our vector comes from. Ax equals a cosine theta. When we're looking at our y vector, now we have the opposite side, so we have opposite over hypotenuse. So the sine of theta equals ay divided by a. Same thing, multiply both sides by a to solve for our y component. So we have ay equals a sine theta. So that's how we would find the components of our vectors, the individual components of our vectors. So of course, when we add vectors, we have two vectors we're adding. So we would have one vector we would call the a vector, and we would use these formulas. And we would have our second vector that we would call our b vector, and we'd use these exact same formulas, but we'd say bx equals b cosine theta and by equals b sine theta. So this is what it looks like mathematically, right? We had this 40-degree angle, right? So cosine of this 40-degree angle equals our adjacent side, f of x, divided by our hypotenuse, 60. So we solve for f of x. F of x equals a, which is 60, times the cosine of theta, which is 40. So that gives us how far over we went in the y direction. So that's called, I'm sorry, in the x direction. So that's the x component of our a vector, okay? Then we do the same thing for the y, how far to go in the y direction, and it's just a sine theta, right? So for x, it's a cosine theta. For y, it's a sine theta. But remember, there are formulas, so they'll be given to you. You don't have to memorize that. And then do your math and you solve for the y component of the vector, how far you went on the y-axis. So these are, you can think of the components as if you shined a light onto your vector, how much shadow would it have on the x-axis and how much shadow would it have on the y-axis? Which means that if I had my vector completely on the x-axis, then there would be no shadow on the y-axis, so my y component would be 0 because there's nothing on the y-axis. It doesn't go up or down at all. And I'll show you that in a little bit too. So why bother doing this? We do this because now we can take those individual pieces and we can add them together to get the pieces that make up our resultant. So I put in ax plus bx plus cx here. We're only going to be adding 2 vectors, so all we'll need is ax and bx. But I wanted to put this in to show you no matter how many vectors you have, you can add up the components of all the vectors, and when you add them together, it gives you the components of your resultant. So you'll take your ax and your bx, just add them together, no fancy math, add them together, and that'll give you the x component of your resultant. And then add your y pieces together, and that'll give you the y component of your resultant. The reason that we want to do this is because if we have the x and y components of our resultant, they're at 90 degrees to each other. The x and y components, because they're on the axes, are always at 90 degrees to each other. So now if we have the x and y component of our resultant, and they're at 90 degrees to each other, now we can use SOHCAHTOA to solve for the angle of our resultant. And because we have the x and y axes, those 2 sides, those 2 components, that means that we have the opposite and adjacent side. So that's where we get that bottom formula, tan theta equals our y component of the resultant divided by the x component of the resultant. And that's how we can find the angle of our resultant when we have a non-90 degree angle. So I'm going to show you a picture of what this looks like. And I'm going to be honest, I feel like this is a little bit confusing, so I'm going to show it to you in action in just a minute, but I wanted to walk you through when it's all done out for you. So here's our A vector and our B vector. Okay, so those are the like teal kind of colors here. So normally what we've done is say, okay, so here's our resultant, and we can use law of cosines to find that resultant. But now we're saying, well, we want to know the angle of that resultant. And the only way to do that is to first find our components ax and ay. So those bright green lines are the components of this vector. Then we go to our b vector and find bx and by, which you can't really see, it's hidden there. But bx and by are the components of our b vector. Then we can take ax plus bx. So see, if I brought this bx down here, see how it would add up, and that would be the x component of our resultant. And then ay, if I brought this over here, ay plus by, see how putting those together gives us the y component of our resultant. So ay plus by gives us the y component of our resultant. And now you see those 2 lines, our x and y components of our resultant, are at 90 degrees to each other, right? So now I can use Pythagorean theorem, use tan theta equals ry over rx, and that will give us the angle right here. That'll give us the angle of our resultant. So we can actually figure out the angle of our resultant even when our 2 vectors aren't at 90 degrees to each other. So to show you what that looks like in action, it might be a little bit easier to see this way. If I have a vector like this, you see the components, right? As I move this vector, watch how the components change. If it's pointed this way, notice I have a negative x component, but I'm still in the positive y direction. If I move it down here, now it's in the negative x direction for my x component, and negative y direction for my y component. So you want to make sure that you draw an accurate sketch in the beginning so you can see if your components are positive or negative, right? And depending on which quadrant in, right, I go in the positive x direction here, but the negative y direction. So depending on the quadrant will change if your components are positive or negative. So if I had two vectors, right, tip to tail, so I put this one here, and normally I would have, right, we've been finding this sum here, this resultant, we've been finding that using our law of cosines, which we can still use the law of cosines to find that 22.6, the magnitude, but that won't give us the angle. That won't give us this angle down here, right? So to get that angle down here, right, if I move this, we would need to find these two components, right? And to find those two components, we need to add up the components of our two vectors, right? So if I move this over here, you see how the components all move? So the components of this one, here's the x component, here's the y component, and then the components of my resultant, same thing, those moved, right? So it's just the two x components added together will be the x component of my resultant, and the two y components added together will be the y component of my resultant.